So I'm putting titles now for you. Okay, so on Tuesday, we talked about the beginnings of probability, and we were talking about addition rules for probability. Now we're going to talk about multiplication of probability, which is actually more common in things. So figuring out, like we were talking about, like the lottery and stuff like that. We're trying to figure out how many possible combinations are in their lottery. That's a multiplication step because we have multiple steps that are related to each other. We're not adding a bunch of combinations together. So the first thing we need to look at is, are the two events independent or dependent on each other? So Hawks gives you these crazy definitions. And honestly, in this section, some of the definitions I think make this a way harder than it has to be. Independent and dependent is simple. If the one probability doesn't impact the next one, they're independent. So, for example, if I roll a die and I flip a coin, whatever I roll on the die has no impact on the coin. Okay? Or like when we were talking on Tuesday about roulette, if I spin the wheel and then I spin the wheel again, there's no impact on it. They're all independent events. However, if I have a deck of cards and I take out a king and I try to pull out a queen the next one, that me pulling out that king and still holding onto it impacts the probability of me pulling out a queen or a king or everything else in that deck because the amount of cards in that deck changed. So that's the difference between independent and dependent. I hate their definition because it looks more complicated than it has to be. Okay? But I put it there because it's nice to know. Yes, go ahead.
Well, let me say, are you about to explain law 10? Because it's basically says
Yeah.
the same thing. Okay.
Yeah. So law 10 is basically saying if they are independent, I can just multiply the probability of each independent event together to find the probability of the total events. We did this actually the other day. We were talking about the option was, actually, I'll just do it in this slide. We were talking about flipping a coin, right? And I said, okay, what's the odds of me getting a heads on the first coin? Was 1 out of 2. What's the odds of me getting 2 heads in a row? And it was 1 out of 2 times 1 out of 2. And we got 1/4. Remember that? Vaguely? I think we got 1,000, and I think it was like they wanted 10 heads in a row, and it was 1 out of 10,000, 1,000. That's multiplication because we're taking each of those probabilities and we're multiplying them together to figure out the probability of that one event happening. So let's look at one. So we have a coin is flipped, a die is rolled, and a card is drawn from a standard deck of 52 cards. Now, I do not know how Hawks is going to do it because I haven't actually looked. However, how many face cards are in a deck of cards? How many face cards? Okay, let's take a step back. What is a face card in a deck of playing cards? Right. It's the king, the queen, and the jack. Those are your face cards. The ace is not a face card. We had to go back and forth so many times with me and this group of math teachers writing these books. We were talking about probability because everybody had a different opinion on what a face card was. So we ended up having to literally write in the problem face cards, parentheses, jack, queen, king, because not everybody knows what the face cards are in a deck of playing cards. So a standard deck of playing cards, the face cards are a jack, a queen, and a king. So if any question asks you that, that's what you would expect to use. Okay, now let's go back to this problem. So, and a 52 deck of cards doesn't consider the 2 jokers because that would be 54. So we've got what's the probability of getting a tail on the coin, a 5 on the die, and a jack of clubs from the deck of cards? Are these, first off, before we can do it, are these independent events? Yes, because the coin, the die, and the cards do not impact each other. They are all independent, distinct events. So the coin, what's the probability of actually, let me actually write this the proper way so you can see exactly how these are going to be read. So the probability of tails is what? 1 out of 2. The probability of a 5. 1 out of 6. As long as it says a die and doesn't give you any qualification, it's a standard 6-sided die. Okay? If they want a different size die, 10-sided, 20-sided, 4-sided, whatever else, they will say that number-sided die. So if it just says die, expect it is a standard 6-sided die. And the jack of clubs.
That'd be 13 out of 2.
No. That would be clubs, but not a jack of clubs. How many jacks of clubs are there in the deck? 1 out of 52 cards. So the probability of all these happening, the probability of tails and 5 and the jack of clubs, we then multiply 1/2 times 1/6 times 1/52. So 1/2, 1/6, 1/52. I think they typically want these as decimals on so this one would be 0.0016. That's the probability of getting a tails, a 5, and a jack of clubs. The 1/624? I don't know, actually. I haven't actually tried.
Typically does, at least in this
Okay.
last practice section.
It what? Okay, I'll take the fraction, then leave it as a fraction. Yeah. So that's where Desmos comes in, because if you multiply it in Desmos and you click that, that's always the most simplified form. Okay. So if you put them in, it'll give you the decimal. Just click the little fraction button next to it. It'll simplify your fraction for you. Okay. So nice, easy. Use Desmos scientific calculator. Definitely helps you. Okay.
What kind of words you'd say that's like you have a 0.0016% chance?
No, you'd say 0.0016. It's a probability of 0.0016, not percent. You'd have to move the decimal place 2 places to make it a percent. It'd be 0.16% chance.
Okay, okay. That's it.
Yeah. Okay. That makes sense? This works if it's independent. No. Complement would be the exact opposite of it. So when I said, let's take the die. Rolling a 5 is 1/6. The complement of that would be rolling not a 5, which would be 5/6. That's the complement. It's the opposite. All right. Choose 2 cards from a standard deck, replacing the first card, shuffling before choosing the second one. Why is that part so important to what I was talking about? Huh? Right. That makes it independent. I choose the card, I put it back in, I shuffle, I choose the next card. Therefore, the first card has no impact on the second card. So now the 2 events are independent. What is the probability of choosing a king, then a queen?
That'd be 13 and 15.
Nope, that's the suit. How many queens are there in the deck? There's 4. Oh, sorry, I did king first, but that's okay. So there's 4 out of 52. for my queen. How many kings? Same thing, 4 out of 52. So I would multiply 4 out of 52 times 4 out of 52, which, yes, is 1 over 13 if you wanted to reduce it beforehand. But like I said, Desmos will do it for you, and it saves you from possibly making a mistake reducing. So you can see this. I did the 4 out of 52 times the 4 out of 52. It gives me this nice long decimal. Click that button there, and it gives me out as 1 over 169. So it'll give it to you in the reduced format. This class isn't teaching you how to reduce fractions, so I'm not worried about you reducing fractions. Use technology. So 1 out of 169. If they didn't shuffle and replace the card, then they would not be dependent or independent. We'd have to do something slightly different for it.
Would the slightly different be what we learned yesterday?
Similar, except we were adding instead of multiplying, but yes.
Okay, so we have already learned what we would have done.
Well, we learned what we're going to do, yes, but then we're going to actually put them together to actually multiply to get the final answer. So yes, yes. All right. So whenever we talk about probability, we always tend to go to games, dice, coins, cards, things like that. Oh, actually, talking about coins, and I don't know if this is just the fact that literally I was searching stuff and Google put it up on my feed, or if it actually became things. Do you know flipping a coin is not fair? No, it has nothing to do with the weight. So a person wanted to determine if flipping a coin, so we always flip coins and it's like, okay, you do enough of them, it's going to come out to be about 50-50. They wanted to determine if the face that was facing up when you flipped it is more or less likely to come out when you flip the coin. And what they found was that it is. Whatever face is on top when you flip the coin comes out about 1% more often than the other side. Now, it's not drastically different, but it is enough to make statistical difference if you do enough of them. So if you're going to sit there and go out, like, pick a side when you're flipping a coin, look at what side the person's flipping it with. Pick that one. I found that interesting because I'm like, we were just talking about this. It's probably Google and everybody else listening like they normally do and throwing it up in my feeds. All right. So not everything has to do with games, though. So when we're looking at product or production and stuff like that, we have to figure out the probabilities of things that are going to be defective. Okay. So any kind of production process has a certain percent where the part, like, it's an acceptable defect rate. Okay. So for example, I do 3D printing and I sell my products and I make dragons and stuff like that. And I sell them. I expect a failure rate of around 10 to 15%. So out of 10 dragons I print, I'm going to expect at least probably 1 or 2 of them to fail. Okay. Which means I have to put that into my cost because that's stuff that I'm not going to be able to sell. I have to throw away, but that's still money I put out. So anytime you produce something, you have to keep into that process. So what they want to know in the first question is, what's the probability that all 4 parts are defective? So they gave us the probability that they are non-defective. Okay. So part A is good 0.9% of the time, or 0.9, not percent. I did it. What's the defective rate? If 0.9 is the good rate, what's the defective rate? Yeah, 0.1. That's what you were asking before. What's the complement? So you typically would see that with the little C up top. I think that's what Hawks is using. So that's 0.1. B is 0.7. So its complement would be 0.3. C, 0.8. So its complement would be what? 0.2. And then D is 0.9, and its complement is 0.1. So what's the probability that all 4 parts are defective? So what do we do now? Yep, we multiply those 4 numbers. And we get 0.0006. So we've got a 0.006 probability that the, or point, yeah, 0.006, that all 4 parts are defective. Okay? Does that make sense? Okay. Next question.
So the 0.006 is the probability of them being defective.
That's all of them being defective. Yes, that's
Okay.
that's the A. So 0.0006. No problem. All right. Next question. What's the probability that the product does not work? So for this one, in order for the product to operate properly, each part must be free of defects. So all 4 parts have to be perfect for the part to work. So what's the probability that the product does not work? Huh? Well, if I add them all up, I'm going to get over 1, and probability has to be between 0 and 1. So that would work. How would I figure out if the probability that the product does not work? All right, let me ask a different question. How would I figure out if the probability of the product does work?
You would multiply all of those up there?
Yeah, because that would tell me if each one works, right? So the probability that each one of those works is there. To find the probability that it does work, I just multiply those 4. Yeah.
If you find a probability of it working, check that.
Yes, that's what we're going to do. So remember, we can do it both ways, right? If we're looking for the opposite, we can then just take that away from 1, and whatever left over is going to give me the percent of what I want. So one of the questions you asked before, they wanted to say greater than 5 or greater than 4 was on the sum rules. Like, okay, you could have added up 5, 6, 7, 8, 9, 10, 11, and 12, or you could have added up 1, 2, 3, and 4 and subtracted it from 1. Both those would have given you the exact same answer because they're complements of each other. So in this case, I'm going to multiply those 4 numbers. So 0.9 times 0.7, 0.8, and 0.9. So 0.4536. So that's the probability that it will work or it won't work. That's the probability that it will work. So what's the probability that it won't work? I have to do 1 minus that. And I get 5464.
Why is it -1 then?
One's the whole, right? So if I have two options, works and doesn't work, I found one of the options, the other option has to add up to the 1. So I subtract 1 from it, gives me the complement. That's in essence what we did when we were looking over here. We were taking the complement of each of those. So if it's 90% works, 10% doesn't work. Because it adds up to the 1. Yes.
Okay. I see that we got different numbers, but like, what's the difference between those?
This works.
Okay, let me rephrase. Between
Yeah.
that, between part A and part B.
Oh, the first one was asking if all 4 parts are bad. The second one, it's based on the directions, said that if one part's bad, the whole thing doesn't work. The first one was saying all 4 have to be bad. So we in essence would have had to figure out what's the probability of all 4 being bad, what's the probability of 3 of them being bad, what's the probability of 2 of them being bad, what's the probability of 1 of them being bad. Because in any of those situations, this wouldn't work. So what we did, instead of having to figure it out that way, because that would have been a pain in the butt, we figured out, okay, let's figure out what happens. What's the probability of it working? What's the probability of all 4 parts being perfect? And that's just multiplying those 4 numbers.
Okay, and then
we just subtracted it from 1 because we want the opposite of that. We wanted not working.
Okay, I get that.
Okay.
Because in my head, that's why I was sitting here confused, because I was wondering why we weren't figuring out the complicated way.
Yeah, because it's one of those things that if it was just all 4 parts had to be bad, that would have been simple. We figured that part out. We did it. The problem is that the way this is worded, any one part being broke throws me out. So there's so many possible combinations that I would have to figure out. It's easier to find what works and then just subtract it from 1. So yeah, this production process has almost a 55% failure rate.
Dang.
Yeah.
That's very.
Yeah, this is one of those word problems that's not realistic. But that's what happens when sometimes you make up numbers with math problems. All right. Questions with this? Okay. I'm going to do this one next. Then we'll go back to complementary. All right. This is probability law 11, and if they're dependent, I wouldn't go through this whole work. You just have to take that away from it. So for example, and this is what I had already talked about when we did the addition, because we kind of used the same concept. What's the probability of drawing a king out of a deck of cards? It's 4 out of 52. What's the probability of drawing a king, a queen, knowing I've already drawn the king? How many queens are left in the deck? 4. And how many cards are left in the deck? 51. Okay. So it's this really complicated equation to do something that I think you could figure out how to do. Okay. So if you remove something from it, it impacts the rest of them. These are when they are dependent. Yes.
I have a question. Why would the second one be 52? If there's like 4 kings you take out, would that be like?
I'm not taking out. I'm taking 1 king out. Yeah, it says I drew a king. So there was 4 kings and then I drew 1 of them. So there's only 51 cards left in the deck, but there's still 4 queens. If I was to say 2 kings, so actually let's finish this one real quick. So it's the probability of a king times the probability of a queen, given that I already drew the king, is 4 out of 52 times 4 out of 51. So 4 out of 52 times 4 out of 51 is 4 out of 663. Or 0.006. If I had said 2 kings, what would the second fraction have been? The first fraction would have been 4 out of 52, right? That wouldn't have changed. What would the second one have been? How many kings are left in the deck? 3. How many cards? 51. So it would have been 4 out of 52 and then 3 out of 51 because I already pulled the king. Okay, does that make sense? You see the difference between those two? Okay, so when you're thinking about it that way, you have to kind of figure out what's going on with that respect. Yes. I didn't kind of really have an exact one. I said you just have to actually figure out the next definition based on what left the first one. I didn't have a literally written out rule for it. You can take a picture of that one.
Yeah, I just took them over. Thank you.
All right. Assume there's 17 men and 24 women in the Lions Club. 2 members are chosen at randomly each year to serve on the hospitality committee. What's the probability of choosing 2 members at random, the first being a man and the second being a woman? So first off, are these independent events or dependent events? Why?
Because they're pulling men and women at the same time. They're pulling the whole school, which includes men and women, so they're doing it kind of same. Like,
Yeah, okay.
so-
All right. Anybody got it better? You're not wrong. Okay, but that could be independent too. What makes it dependent and not independent? Yeah. Right. Once I pull one out, the population decreases. Okay. So that changes the probability of the next one happening. That's what makes it dependent. Okay. So what's the probability of me pulling a man for the first one? So 17 out of 41. And what's the probability of me picking a woman for the next one?
24 out of 40.
24 out of 40. Okay. So we multiply them. And we get 51 out of 205. Or this one makes more sense as a percent, approximately 25%, 24.8%. Okay. Does that make sense? Yes? No? Okay. One more to go. Well, we got a few more to go. One more before I get into permutations and combinations.
Okay, just to confirm with the last one, the reason you have one less.
In the population?
41 is because you.
I took away the first man.
Okay, yep, then that makes sense.
Yep. As I said, when you're dealing with cards and like things like that, it makes it really, it's like, oh yeah, it just makes sense. Like once you move out of that realm and deal with something else, like, does it actually change? Like, yeah, that person is no longer part of the pool that I'm pulling it for. So technically those 24 women have a higher percentage chance of being pulled than they did before because there's one less person in the pool to be pulled from. All right. Conditional probability. So conditional probability is when I want to know an event occurring given that something else has occurred. Okay, so it's similar to what we were just talking about when we were talking about, well, we pull a card and the king is out. And that's where that little bar was. It stands technically for conditional probability. You very rarely use it when you're dealing with dependent probability just because it's easy to figure that out yourself. Where it does come up into play is things such as this. When you're looking at a table of values and you're pulling information out of it. So if I wanted to figure out what's the probability of an 18 to 34-year-old liking whatever this product is. Okay. What's the probability of an 18 to 34-year-old liking this product? Yes. Anybody. What's the probability of it? Well, okay. How many 18 to 34-year-olds like this product? Good. And if I was looking for probability, it'd be 213 out of the total, right? The 1403. So if I was just doing 18 to 34 that likes it, so I would do the 213. It stopped me writing it. I don't know why. So I would do the 213 divided by the 1403. And that's just because I'm looking at that one right there. Okay? What happens? So the question is if an individual is between 35 and 50, what's the probability that she will like the product? So in this one, I looked at that one and the total. In this, I'm given that they're 35 to 50 years old. So I'm not looking at the total. I'm only looking at the 35 to 50-year-olds. Because we're given that as a fact. I know they're 35 to 50 already. What's the probability that they will like the product is now out of 193. So this one's going to be 193 over 444. That's what a conditional probability is. So I've already given you one condition. Now, what's the probability that something else is going to happen given that information? Okay. So we could go the other direction. What's the probability that if they did not like the product, they are over 50? So I'm telling you, if they didn't like the product, what's the probability that they're over 50?
Not like the product.
They didn't like the product,
So the 219
and they're
over the 4.
no. What was the initial thing? They didn't like the product, right? So that is going to be where I'm getting my total.
Oh.
So it's a 600,
Over.
and then over 50 is 219. So it's 219 over the 600. So it does matter the direction that you're saying. It matters what the condition is. Okay. So in this one, the one they gave you, they said the condition was 35 to 50. That's why I used the 444. Because that was the initial condition. And out of those, they liked it was the 193. The one I gave you, I said the condition is not likely. We're not liking it. And then I said, what's the probability that they're over 50? That for the total is 600, and it's a 219 over 600. Okay? So when you're looking at conditional probability, that's where that condition comes in. That's going to change your total piece out. Okay? And that's why when they were talking about the dependent probability, they were dealing with that because it's okay. The condition was, I already drew a king. What's the probability I'm going to draw a queen? Now 4 out of 51 because I already drew that king. It changed things. That's why they used conditional probability, but you don't typically use it like that outside of this. All right. Any questions on these? Let's do a problem. Actually, not going to do that problem yet. I'm going to get to that one. We're going to figure out the odds of winning the Powerball today. Somebody won it again in California. Again in California. Well, not one person. One ticket. They don't know how many people, but one ticket won it. Yes. So, all right. Anybody ever heard of permutations and combinations? Anybody ever see that button on your calculator that's like it's NCR and NPR? There's those two little buttons on your calculator. Combinations and permutations. All right, that's what we're going to look at. So we're going to look at three different things with this. So what I just covered was 6.3. This is 6.4 if you're keeping track of your sections. The fundamental accounting principle says if I have a list of combinations, I can multiply the probability of each of those events and find the total probability of that happening. That's the multiplication one. Accounting principle says I can do that to figure out how many options I have. So I would use this to figure out the total on the bottom. And then I can use that to figure out the probability. So let's see how this actually works, and it'll make total sense. A local office supply store offers ballpoint pens from 3 different manufacturers. Each ballpoint pen comes in either red, blue, black, or green, and either fine or medium tip is available of each color. How many different pens does the store carry? So you could sit here and try to list out all the possible pens, which you could do with like a nice little tree diagram. Or we can just look at it as I have 3 manufacturers. How many colors do I have? I have 4 colors. And how many tips do I have? 2. So I have 24 different pens. That's it. That's the fundamental accounting principle. That's why I said, like, isn't there go through and read it all? It's like, that sounds complicated. That's the fundamental accounting principle. That's all you're doing. If you've ever planning a wedding, you're going to deal with this on a regular basis. Because you're going to go, okay, I have this many appetizers, this many entrees, this many desserts, and then you figure out like, oh, I have 500 different possible plates that they can get. I'm just going to go for a buffet. It's like, but that's in essence what they're doing. It's like you're looking at all the possible combinations. Okay. So that's the fundamental accounting principle. All right, let's look at the license plates in Connecticut. They've changed. It used to be 3 numbers and 3 letters. Now it's 2 letters and 5 numbers, not including vanity plates and all the other stuff. So how many different license plates that they can have in the state of Connecticut that has 2 letters and 5 numbers? So how many letters are there in the alphabet?
Wait, 26? Wait. Am I close?
It's 26.
Okay.
You got it the second time. It's like, it's not a hard question, guys.
I mean, it's 7:40, and I'm going to throw a lot of information at us. I will say this in her defense. You ask a question like you asked in the last, and it's super freaking easy. It's something that's supposed to be straight.
Okay.
That's another one.
So there's 26 letters. I have 26 letters. I have 2 of those, right? They can be the same letter. So I have 26 letters for my second one. Now I'm going to ask the confusing question. How many numbers can be in the next one? Very good. They didn't get that one wrong. They got the letters one wrong, but that's the numbers one. There's 10, 0 to 9. And there's 10 for this one, and there's 10 for that one, and there's 10 for that one, and there's 10 for that one. Your license plate, 2 letters. Letters. 5. Because they can repeat. I can have AA 000000. That's a possible combination of letters. So we just multiply it. And we get 67,600,000. That's how many different license plate combinations they can make. Now, normally they have some rules, like they don't typically use Qs, they don't typically use Os, because those can be confused as numbers and letters, because they want to make the license plates easy for the cops to read. So it's like they won't have the confusing ones in there. So there might be a little less than that, but that's when you go through it. That's what you'd do. Yeah. So, okay. That's the fundamental accounting principle. Really complicated concept made really simple at 7:40 at night. All right. This nice little crazy formula down there. We're never using it. You're going to use that NPR button on your calculator. We've got permutations and we've got combinations. Okay. The only difference between them is order. Okay. If order matters, then it is a permutation. If order does not matter, it is a combination. Okay. So I will write this out so you can see this, because this is the most important part. Okay. Order matters, NPR. Order does not matter, NCR. So if I'm going to take a group of letters and try to make a name, does order matter? Yes. Order matters in that situation, right? Because ABC is different than CAB. Those are 2 different things. One's a word, one's not. Those are 2 different things. So order would matter in that situation. If I'm pulling 5 cards out of a deck of playing cards, does the order I draw those 5 cards out matter for the hand that I have? No, your hand's the same. So order does not matter in that situation. All right. So your goal to figure out which one it is literally to determine if order matters or order does not matter. And then you're going to use the form, the way you're going to type in the calculator is exactly the same. It's just a matter of which button you're going to press. So a local fast food restaurant, the door to the kitchen is secured by a 5-button lock labeled 1, 2, 3, 4, 5. To open the door, the correct 3-digit code must be pushed. Each button can only be pushed once. How many different codes are possible? Why?
Because it's 3 digits, and then there's 5 numbers. But you can only, oh wait, we can only type the 1.
You can only use the number once. So first off, let's make this simple. Does order matter or not matter? When you type your PIN into your phone, does the order matter? Yeah, this is a code. It's order matters, right? 1, 2, 3, 4, or 1, 2, 3 is going to be different than 3, 2, 1. Okay, those would be 2 different passwords. So order does matter. So we need permutation. So we're going to use NPR. Now, depending on the calculator you're using, sometimes you have to put the numbers in and then hit the NPR and then hit the other number and put just a P there. Desmos puts them after it. So I'm going to show you the way Desmos does it, but it doesn't make much difference. I'll actually write them both so you can see them both. All right. How many numbers do I have? 5. How many numbers am I choosing? 3. So it's 5 T3. So we go to Desmos. So first off, everybody understand where the 5 and the 3 came from? Okay. So under function, right here, NPR and NCR, we're using P because order matters. So the 5, choose 3. 3, choose 5. It'll yell at you. Because how can I choose 5 numbers if I only have 3 to start with? True? So it won't work.
Would that work with the NCR because the numbers don't matter
Order matters.
or
Order doesn't matter in NCR.
so
I still can't do 3, 5.
Okay.
Big one always got to go first.
Okay.
They can be the same, but the big one's always got to go first. Huh? Yes, no matter what. Because again, it's basically how many you have and you're choosing how many. So I have 5 choosing 3. 5 choosing 3 because you guys are looking backwards from me. So the big number's always got to go first because I can't choose more than I have. Okay, so there is 60 combinations of this. That's it. That's permutations. I have 7 sprinters that are in the final heat of the track meet. How many different ways can they finish first, second, and third? So, does order matter?
Yes.
I think the person who comes in first wants the gold medal. So order would matter. So yes, order matters in this situation. So I have NPR. I have 7, and I'm choosing 3. So there's 210 different ways the race can end. Try this on whatever calculator you plan on using to make sure you can get 210. Because if you don't, then I have to show you how to use your calculator, which is fine. Totally can do that.
That seems like, I mean, I understand, but that seems like a really good number at the same time.
Because you got to remember, it's like, so if you think about it, how many different, so we can, this one's actually easy. We can do this one out. How many different people can finish first place? How many different people can finish second place? Right, because there's already one person finishing first. How many people can finish in third place? 5. So what's 7 times 6 times 5? 210.
Okay, thank you. That's what I needed to understand what we were doing. Thank you.
Now, permutations allows us to do drastically larger numbers in different combinations. So it's like, yes, these two are very simple situations where I could actually calculate it out by hand. But permutations allows you to do a lot more than that.
It still gives a visual.
Yes. Yeah. And actually, that's a very good. So let's say it wasn't first, second, and third. Let's say this is the US trials and the top 3 people go to the Olympics. In that situation, does order matter? No, because all 3 are going, right? So it doesn't make a difference who finished first, second, and third. All 3 are going to the Olympics. So order doesn't matter in that situation. So then we would have to use combinations. We would have to use the combination because order does not matter in that situation. So we would use NCR instead of NPR. Okay. So let's actually do the one I just did. All right. So if it didn't really matter if they came in first, second, or third, we just want 3 people. The process is exactly the same, except this time I'm using NCR. So it's going to be still 7, choose 3. Yes, 35. So in this case, there's 35 different combinations of my U.S. Olympic team. Okay. See the difference between the two? Order matters and order doesn't matter. Okay. Yes.
Did you do that out like the last one? Would that
No.
Would that just be like the 7?
No. It doesn't work that way. Because for example, so 1, 2, 3 and 3, 2, 1 are exactly the same option. So in this case, to get this one, you'd have to list them all out
Okay.
and choose the possible options.
Okay.
So there's no way to do this. That's the big difference between permutations and combinations, because permutations, you can technically still use the fundamental counting theorem because it does work. The permutations just makes it faster. Combinations, you can't. It doesn't work that way because you have that mix up in there that 1, 2, 3 and 3, 2, 1 are both the exact same thing, and using the other process, they're going to count them as 2 different things. Okay. So a little more complicated. All right. Let's look at the lottery. And then we'll do the Powerball. All right. So in South Carolina, Palomino Cash, we have the same thing up here. A player selects 5 different numbers. Has that it? Okay. Does everybody in here know how the lottery works? Okay. If you go to the store, they give you the little piece, and you can pick your quick pick or you can pick your numbers. You can't pick the same number twice. It depends on the lottery. I think the Connecticut one's 1 to 55. Powerball is actually higher than that, I think, now. So they have to pick 5 numbers from 1 to 38. If the number selected matches the player's numbers in any order, the player wins. So what is the total number of winning combinations? So does order matter or does order not matter? Order does not matter. That's why when you pick your numbers on the card, they're always in numerical order on your tickets. No matter how you pick them, they're always in numerical order. However, if you watch the lottery, there's a ball that comes out of a machine, and those do not necessarily come out in order because it's just a randomized ball. So order does not matter in this situation. So we are going to do what? Combinations or permutations? Combinations. So C. So we have 38 numbers, as we are choosing all the numbers from 1 to 38. So that's 38 numbers. And we're choosing 5 of them. So we got 501,942 possible combinations. All right. What's the probability of winning? How many combinations of numbers win? If you're going to win the jackpot, what do you have to have? How many winning numbers, though? You need all 5. So there's 1 out of the 501,942. So that's your probability of winning. Okay. All right. Now, let me see if I can find the exact rules for the Powerball, because honestly, I haven't looked up in a while. All right. So here is the rules for the Powerball. All right, so the Powerball, you want to select 5 numbers between 1 and 69, and then select one number from 1 to 26, also called the Powerball. So let's look at this. Let's look at the first part first, the 1 to 69. Does order matter? No. So that's going to be a combination or permutation. Combination, C. So I have 69 balls, and I'm choosing 5 of them. So we got 11,238,513. 238,513. All right. However, they have that Powerball there. And you pick one of those numbers, right? How many numbers can you choose? 26 of them, right? So I have to multiply this by 26. Which gives me 292,201,338. 292,201. 292,201. 338. So your probability of winning the Powerball is 1 in 292,201,338. There is a chance. Okay. So they've changed the Powerball over the years. This is why it's starting to get a lot higher numbers now, because what they found is that people don't play it when it's like $20 million. People play it when it gets up into like $500-600 million. That's when they start to play. So what they found was if they get the numbers to creep up there, where they make more money, because they don't give every dollar out that they go into it. They keep more than half of it actually. So they changed the numbers. If they change this, just this number right here, from 20 to 26, they just added 60 million different combinations to it. So if I took that number, that 26, and changed it to 30, we're now looking at 337 million different combinations. So, and if they decided to change that 69 to a 75, we're now at 448 million. So they can make one little change to this, just add a few extra numbers, and drastically decrease the odds of you winning. But what that does is it increases the jackpots, and more people are going to play, which then in terms makes them more money. And all your lotteries are run by the state, so it's basically you're just giving your money to the state. That's why they call it a tax on poor people, because the vast majority of people that play it don't have a lot of money. The Massachusetts lottery, their odds were actually low enough that at one point the jackpot had gotten so high because nobody was winning it that somebody was able to actually get a group of people together to go buy every single number of ticket for the lottery. So they had every possible combination of ticket. They spent like $3 million on it, but the jackpot was like $10 million. They were guaranteed to win it. So what did the lottery do? They just increased the numbers. They increased the odds, so they couldn't do that anymore. And they put rules in that said you can only buy 100 tickets at a time. So, but if the odds are low enough, people actually do that. Right now, it's 292 million. The jackpot was 1.7 billion. Even if you take out the lump sum, you're getting $600 million after the lump sum and the taxes and everything else. It's double the odds. If you could come up and figure out a way to buy all 292 million tickets, you're guaranteed to win and double your money. Yeah. Like, let me start counting out my ones. Okay. So the problem is it's just physically impossible to do that nowadays. All right. So what's the difference between combinations and permutations? Very good. Have a wonderful weekend. Oh, we finished chapter 6, by the way.
Oh, no, I thought you were back in the I'm like, wow, that's low even for you. I was like, that's low.
You need to send me back the ones you did and tell me which ones, and so I can send you the next set of them.